Welcome back. So now we continue our discussion on modeling reverse transcriptase inhibitors, okay? And this will be the second part of our conversation. We were talking about simulations, and we will resume with more simulations. So the simulations we were discussing had to do with numerical solutions for these equations here, and we were discussing for two extreme values of eta equals 0 and eta equals 1. So let's continue that conversation. So what we had seen before were two scenarios, one in which there is no treatment, or the effectiveness of treatment is equal to 0. That's analogous to not having any treatment. And we can test here the numerical solutions are giving us solutions for a stable equilibrium that's called endemic equilibrium. But when treatment is applied in full force, that is in a schedule in which the drug is 100% effective, it's possible to perturb that equilibrium, and basically the solutions leave the basin of attraction of a stable endemic equilibrium and they converge into what's called the basin of attraction of a stable disease-free scenario. Okay, and that steady state will see populations of virus and infected cells converge to 0. This is a very idealistic scenario, and would like to comment here on some other scenarios that are intermediate cases for where treatment is not 100% effective, but rather is only partially effective. So here is an illustration of something like that. What if the interaction term was reduced only by a factor of 1/2? In other words, what if that effectiveness were something in the neighborhood of 50% of effectiveness? There'll be a reduction in beta from its original value to 1/2 of its original value. So what you can see here is that we observe patterns that are consistent with still stable endemic equilibrium. The uninfected cells remain there at that equilibrium level, coexistent with the other ones. There may be a little bit of a different shape here, however. We can maybe compare that with the initial case when there is no treatment, and you can see that these curves, both the amount of virus and infected cells, are kind of sharply growing, very steep. There is a slope here, they steeply grow, right? And you would argue that this scenario here with partial effectiveness of treatment only 50% is basically the same as when eta equals 0. Well, basically, because you still have a stable endemic equilibrium, but that seems to start already playing a role with the shape of these curves on the initial time points of the simulated scenario. What happens if we now consider the value of, instead of 0.5 for eta, the value of 0.75? That would correspond to 3/4, okay? And you can see how you still have solutions that are typical of a stable endemic equilibrium. However, that steepness, that slope is less steep, okay? And that's having an effect here with the slope of the initial growth of virus and the initial growth of infected uh, cells, okay? And if we review, we know what happens as this parameter gets closer to 1. We will be able to perturb that the stability of that equilibrium. But what happens if now that parameter takes a value of like 0.95? And so you observe everything, the only thing that we are changing on these simulations is the value of eta. Everything else, the number of time points, the initial conditions, and all the other parameter values are fixed at the same values. And you see how there is a even more pronounced stretch here. The initial growth is really being compromised, and it's the initial growth of infection being the initial amount of infected cells, the initial amount of virus, is now growing really, really slowly in comparison to the previous scenarios. And if we observe this last scenario in which eta is almost really getting very, very close to 1, we can see how the effect of treatment is really slowing down the growth. Remember that virus will grow proportionally to the amount of infected cells. So if there is not enough infected cells, eventually both infected cells and virus will die out, which is exactly what happens when the disease-free equilibrium is stable. And it's exactly what happens if you set this to be even closer to 1, like 0.99 or 0.978 or something. So this leaves already, this gives you plenty of room to run your own numerical simulations of this very simple model with a very basic modeling of treatment schedules, specifically the reverse transcriptase inhibition. Thank you.